Hello and welcome back to the final speedrun of today. In today's speedrun we will be going over more on modeling real-life scenarios and using calculus in them, so let's jump right in. So the final model or real-life scenario we have to cover is kinematics, which links very well with physics. If you're a physics student, I'm sure you know a lot about this already. But specifically the calculus part, we have displacement, which is the distance an object has moved from its origin. It's a vector quantity. And the derivative of displacement with time is equal to velocity. I'm sure you know that velocity is the gradient of a displacement time graph. And the derivative of velocity over time, which is equal to the second derivative of displacement over time, is equal to acceleration. So we need to know if we derive displacement once, we get velocity. If we derive it again, we get acceleration. And yeah, so that's pretty much it. So now we can jump into some problems. I'll stick to the odd ones for today. So we have the first problem as the height h meters of an object that is moving along a vertical path is modeled by the function h is equal to 112 plus 96t minus 16t squared. Where t is the time in seconds. Find the object's velocity at t equals 0, the maximum height of the object, and the time at which it reaches maximum height, and the object's velocity when h equals 0. Okay, so this is not that hard. So first of all, to find the object's velocity at t equals 0, we want to derive this function. So we have dh over t over dt, which is equal to the velocity, is equal to 96 minus 32t. So when t equals 0, the velocity is simply 96 meters per second. So yeah, sorry, that's the first one done. Now the maximum height of the object and the time it reaches maximum height. So the maximum height of the object will occur when the velocity is equal to 0, because that's when it's reached maximum height. So that's simply when t is equal to 96 over 32, which is equal to 3. So when t equals 3, we'll reach maximum height, and the maximum height will be 112 plus 96 times 3 minus 16 times 3 squared. So the height will be 112 plus 96 times 3 minus 16 times 3 squared. So this will be equal to 112 plus 96 times 3 minus 16 times 3 squared is 256 meters. And finally, the object's velocity when height equals 0. Well, when this height equals 0, we'll have to solve this equation. So we get 96 plus or minus the square root of 96 plus 4 times 112 times 16 all over 2 times negative 16, which is negative 32. So this will be equal to 96 plus 4 times 112 times 16. Square root of this is equal to like 85.2. So it's 96 plus or minus this over negative 32. Is this correct? Negative b, oh, negative b. Negative 96 plus 85. So There's actually going to be two potential values for this. Unless I've messed up the second part of typing. What? Oh, 96 squared. Oh, I'm having an off day. So 96 squared minus 4ac should be equal to 96 squared plus 4 times 112 times 16, square root of all of that, is equal to 128. Since this is over negative 32, we need to actually get the value where we subtract both of them. So we have 96 minus 128. Negative 96 minus 128 all over 32. So we get 7. So when t equals 7, this height will be equal to 0. So when t equals 7, we have 96 minus 32t. 96 minus 32 times 7 is equal to negative 128 meters per second. So yeah, those are the three values that you need to get: this, that, and that. Okay, on to the next one. And the next one is asking us a child toy launches toy rockets into the air. The height h meters of a toy rocket which is launched into the air with an initial velocity of VO and initial height of HO can be modeled by the function h of t is equal to HO plus VOT minus 4.9 t squared, where t is the time in seconds that have passed since the rocket was launched. A toy rocket is launched from the ground with an initial velocity of 50 meters per second. Find the maximum height the rocket reaches. Rocket and the time that passes before it hits the ground again. Oh, I messed it up. Okay, so there we go. And so HOVO minus 4.9 t squared. Toy rocket launched, initial velocity 50 meters per second, maximum height of the rocket. So we know it's launched from the ground, so the function h of t should be equal to 50t minus 4.9 t squared. This is actually a pretty realistic equation. If you ever do physics and you do SUVAT equations, you'll see where this is coming from. Maximum height of the rocket, well, we need to get the derivative of this. Actually, yeah. So maximum height would be 50 dh over dt is equal to 50 minus 9.8 t. So it will be at time 50 over 9.8, which is around 5.1 seconds. So the maximum height, if we substitute 5.1 into this other equation over here, if we substitute 5.1 is 50 times 5.1 minus 4.9 times 5.1 squared. So this is around 2 meters. Okay, and the time before it passes before it hits the ground again. Here's a little trick. If we're modeling with SUVAT equations, it's actually just double this. But that's, you know, that's a very physicsy way of. Oh, hold on. The book is saying that it will actually take 10 seconds to reach the Wait, what? No, that will reach a maximum height of 10.2 meters. Did I make an error? 50 times 50 times 5.1 minus 4.9 times 5.1 squared. The maximum height is not 10.2 meters. I don't know what the book's saying. The maximum height should be 127.4 meters, unless I've made some serious error. And so the time taken is 5.1. Now the book is correct when they say that the time taken to fall back down should simply be 10.2 or like 10 seconds more or less. Because if you think about it, ignoring air resistance, which in this problem it does, if you throw something up, it will take equal time to go up and to come back down again. But in case maybe you don't realize this, let's just quickly prove it over here. We have to get the 0 of this, so 0 is equal to 50 minus 4.9t squared. 50t minus 4.9t squared. So that's equal to 50 minus 4.9t. So t is equal to 50 over 4.9, which is equal to 10.2 seconds. So this is actually correct. I don't know. I think the book's made an error. I don't know. Okay, now on to the next question. Question 5, and that one is, well, we have the position s centimeters of a particle moving along a line can be modeled by the function s of t is equal to negative t cubed minus 3t squared up 3t squared plus 4t plus 3, where t is the time in seconds. Find the velocity and acceleration of the particle at any time t. Well, okay, velocity, acceleration, just get two derivatives. So s is equal to negative t cubed minus 3t squared plus 4t plus 3. Velocity is equal to the derivative, negative 3t squared minus 6t plus 4. Acceleration is equal to negative 6t minus 6. So, if we were to describe the motion of this particle decelerating, or negatively accelerating, I guess. Yeah, so I guess between the interval where the velocity is still greater than 0 but the acceleration is not, then they have different signs. So the particle is decelerating, but past that the particle is negatively accelerating. Yeah. So on to the final question. And the final question is, where is it? A particle moves along a line. So its position at any time t in seconds is s of t is equal to t cubed minus 7t squared plus 11t minus 2.5. Find the velocity and acceleration functions. What has it done? B, find the times when the particle is at rest. C, find the times when the particle is speeding up and slowing down. D, find the values of t when the particle changes direction. And E, find the total distance traveled in the first 3 seconds. Okay, velocity and acceleration functions is the easiest, so let's start with that. By side, velocity is equal to 3t squared minus 14t plus 11 plus 11, and acceleration is equal to 6t minus 14. Times when the particle is at rest. Well, the particle is at rest when, what's it called? The particle is at rest when we have zero velocity. So we can have an acceleration, but we just can't have a velocity. So that's when velocity equals 0. So we have 14 plus or minus the square root of 196 minus 4 times 11 times 3. So that's 11 times 12. That's 132. All over 2 times a is 6. So 196 minus 132 is equal to 64. So it's 14 plus or minus 8 over 6. So the two values should be, let's say 14 plus 8 over 6. 14 plus 8 over 6. 14 plus 8 over 6. There. 22 over 6, so 3.666. And then 14 minus 8, which is of course 6, so otherwise 1. So it should be at 1 and at 3.666. Okay. Next. Find the times when the particle is speeding up and slowing down. So the particle is speeding up as, well, it's going to be in between these two boundaries, really. So let's look at the acceleration. When time is 1, the sign is negative for acceleration. Actually, no, so in between these two bounds. Acceleration is positive when t is greater than 14 over 6, and it's negative when t is less than 14 over 6. So between the times 1 and 14 over 6, let's write this down. Between the times 1 and 14 over 6, this is accelerating. Between 14 over 6 and 3.6, t, this is 22 over 6, the particle is decelerating because it has negative velocity but positive acceleration. Before this time, the particle must have been decelerating, and after this time it must be accelerating. So decelerating, accelerating, decelerating, accelerating. Yeah. So find the values of t when the particle changes direction. The particle changes direction when it's at rest. That's pretty much it, unless you have a function that just touches the x-axis and reverses immediately. Otherwise, it's a root, and so these two values should still be the values for which the particle changes direction. And finally, find the total distance traveled in the first 3 seconds. Ooh. So this is probably an interesting one. We know that there are 2 times where the particle comes to rest. So actually, to find the total distance traveled, we would need to okay. To find the total distance traveled in the first 3 seconds, not knowing any integration, which might come in handy, what would we do? Well, we have the graph of the displacement, And I guess we just need to find the difference between all the minimums and the maximums. We have really here two minimums. So 2 times when the velocity is equal to 0 and the particle changes direction. So this won't be too hard. So we need to find, first of all, how far it travels from 0 to 1, how far it travels from 1 to... actually, hold on. And then we just need to find how far it travels from 1 to 3 seconds. This should be it. So from 0, when it's 0, we're at negative 2.5 meters. And when we get to 1, we're at 1 minus 7 plus 11 minus 2.5. We're at positive 2.5 meters. And then from there, we travel to 27 minus 7 times 9 plus 11 times 3 minus 2.5. We're back at negative 5.5 meters. So here we travel 5 meters, and here we travel 8 meters. So we should travel, I think, 13 meters in total. So yeah, that was pretty much it. That's all for today's speedruns. I hope you enjoyed them, and I hope to see you in the next one. See you then.